Let's look at more with module 7.09 and talk about function composition. We'll see that function composition is different because we're not necessarily looking at an operation symbol here, where we would read this, what we're seeing right here, where we have f bracket g of 4 close bracket. So this is saying that we're taking f of g of 4, f of g of 4. We work from inside out, and we want to figure out what is g of 4 first, what is the g of 4 value, and then take that and figure out what is f of that value. So the main idea here with function composition is to work from inside out. So what is g of 4? We figure out g of 4 by plugging 4 into the g function. Over here, they tell me that f of x is equal to x plus 2. G of x is equal to 2x minus 5. So I'm going to use the g of x function. Instead of saying g of x, we're doing g of 4, which means we're putting the 4 everywhere we see the x. And then we do the math, 2 times 4 minus 5. 2 times 4 is 8, and 8 minus 5 is 3. So we know g of 4 is equal to 3. So now we can come over here and say, well, instead of putting g of 4 there, we know g of 4 is 3. So let's plug in 3 where we see the g of 4. And now all it reads is f of 3. And to find f of 3, you substitute 3 into the f function. So come over here where we see f of x. Instead, it's f of 3, which means we're going to put 3 everywhere we see x. So that's 3 plus 2. F of 3 is equal to 5. 3 plus 2 is 5. So now we just found our answer. F of g of 4 equals 5. So if we do another one and we make sure we are working from inside out, I would start off doing what's inside the brackets here, which is f of 2. That means take the f function, x squared, and do 2 squared to get 4. Now that I know that f of 2 is equal to 4, I can do g of 4. That means take the g function, and instead of doing x plus 1, do 4 plus 1, which is 5. So I've determined that g of f of 2, which is the same thing as g of 4, since we know f of 2 equals 4, is equal to 5. Very similar here, but we're just using a and b to represent our function names instead of f and g. So if a of x equals 4x minus 2 and b of x equals 12 minus x, find b of a of 3. So work from inside out and figure out what a of 3 is first by plugging 3 into the a formula. If a of x equals 4x minus 2, then a of 3 equals 4 times 3 minus 2, or 12 minus 2, which is 10. So now we know if a of 3 equals 10, we can go back up here and say that's the same thing as b of 10, which just means to plug 10 into the b function. And b of x equals 12 minus x, so figure out what b of 10 is, and 12 minus 10 is 2. So my final answer would be 2. You can see this applied with functions that we have to write and model. So let's look at Seth plans to purchase a new phone when they are on sale for 20% off. He knows this discount can be expressed using the function P of C equals 0.8 times C, where P is the new price of the phone and C is the initial cost before the discount. He also knows that he has to pay 11% local taxes on his new phone. The function T of P equals 1.11P can be used to find the total cost of his phone after taxes. Help Seth come up with a function to represent the total cost of any new phone after the discount and with taxes. So we know that the total cost function here is T of P equals 1.11P. But instead of just doing the total, use the total cost of his phone, P, after taxes, we're going to take, and instead of P here, we're going to use P of C and figure out what is the total of P of C, which means take the P of C function and plug it in for P in that other function, which would be 1.11 times 0.80C. And by doing this, we're representing the total cost of the new phone after the discount, because the discounted price is 0.8C, and with taxes, because we're using the function that represents the total cost after taxes, but instead of just using P, we're using the 0.80C to represent the price after the discount. Then when we simplify that, we would see that T of P of C is equal to 0.888C. Another example here we could use is where we have a stone is tossed into the middle of a lake and creates a circular ripple. The radius of the ripple is increasing in the water according to the function R of T equals 12T. So radius, and it represents the R, and T is the number of seconds after the stone hits the water. So the radius of the time, where T is time in number of seconds after the stone hits the water. Now we know that that's our radius based on a specific time is 12 times T. Because the ripple is a circle pattern, the area can then be found using the formula area given R, radius, is equal to pi times R squared. Well, we know R given T is equal to 12T. Instead of using the R in the radius formula, we're going to use R given T, since we know that the radius is dependent on the time. So we're going to come back up here and say, to find the area, we have to use R of T value in my area formula to represent the area as a function of time. So I'm going to take the R of T function, which is 12T, and I'm going to plug that into the area formula, which is pi R squared. So pi times R squared, well, if R is 12T, I would have to do 12T squared. And that's going to give me 12 squared times T squared, which is 144 T squared times pi. I could then take it a step further if I wanted to multiply by 3.14 and do 144 times 3.14 and get an approximate and still be in terms of time.